So thanks for joining me on this journey through the land of source code. We are going to look at AlphaFold, and that's that. That's how things are. I don't know anything about biology. Part 1, step 1, fact 1. First fact, I don't know anything about biology. Second fact, I know barely anything about machine learning in the recent sense. I've spent maybe about 3 days off and on, an hour here or there for the past 3 days, trying to implement some machine learning stuff. For the most part, it's been smooth sailing, but I wanted to take a look at a professional or semi-professional repo so I could get a better sense of what coding standards are like and so on. I don't even know where to start, to be honest. And I'm not even sure what I most want to see. I think that I definitely want to see the model. I assume it's written in PyTorch, maybe. Not PyTorch, TensorFlow. Perhaps there's some JAX here or there. Perhaps everything is JAX all the time. I don't know. But I want to see what that's like. I guess I want to see some of the work that they put into feature engineering. I'm curious to see if there's anything interesting in how they save and load models, although I'm guessing that's mainly just a library call. And so we'll start with that. Images could just be pictures. Okay, so these are just pictures for the website or whatever. So this is something, maybe an experimental result. Okay, so the green is what we know the protein looks like through some sort of experimentation. I don't know what any of this polymerase domain means or whatever. I don't know if these are the same proteins or different ones. I guess they seem different. But then the blue is the predicted result. I assume this is like a best case scenario, but these are very closely matched. That's what they're telling you. That's what they want you to believe, man. Okay. So there's notebooks. I'm guessing these are like Jupyter or IPython notebooks. I don't know if IPython's the same as Jupyter. Run AlphaFold should just be a script to run, probably to do inference. There's a server, which is probably not so fascinating. I assume it uses something like, there's some library for serving models. I think TensorFlow has some server component. I think probably PyTorch does too. And then I guess we can look at the imports. We're using Absolute Python because it's DeepMind, which is owned by Google. And DM Haiku is DeepMind Haiku, which I think is a neural network library. I want to say JAX. In fact, we have JAX down here. ML collections, I'm going to guess, is some Python library of data structures that are useful in machine learning. We also have NumPy and Pandas, standard data science stuff. SciPy, I feel like you see a little bit less often, but it also has a lot of standard algorithms like principal components analysis, I think, is there, and so on. TensorFlow CPU, presumably to support running on the CPU. And then DM tree must be some tree thing. Chex is this must be a JAX library. I forget what they do. And then BioPython is presumably like maybe like bioinformatics stuff. Let's see what Chex is. A library for helping us do something. Right, reliable JAX code. You instrument your code, for example, with assertions or warnings, and you debug, for example, transforming PMaps in VMaps within a context manager. And you test JAX code across many variants. Okay, So that's some testing and correctness library. That's actually kind of nice to see in machine learning. And then the server just has a JSON file. Okay, so I'm not sure what that's about. And then run AlphaFold. I'm pretty sure we can just ignore. It's got a bunch of flags. We're going to parse the flags. You can say some confidence JSON file. I don't know what a confidence file is. And we have predict structure, which might be the main prediction method. FASTA or FASTA, I think is a like a text format for protein stuff or maybe RNA stuff. FASTA protein. I don't think that's it. The FASTA format. In bioinformatics and biochemistry, the FASTA format is a text-based format for representing either nucleotide sequences or amino acid sequences. Okay, and then just out of curiosity, what's up with BioPython? I mainly want to know like what algorithms there are. Maybe API. There's some BLAST stuff. PopGen, which is for population genetics. Whatever PDB is. KEGG. Okay, a bunch of stuff I haven't heard of. I guess it seems like it's mainly organized by the problem domain rather than the algorithm itself. Okay, so we have this predict structure thing. Presumably we're just going to load some stuff. I want to see the model. I want to just jump right to the trace and gun it off. Gun it coming off the line. Okay, it must be in here. AFDB is probably like database. All right, common data model notebooks, Relax. Relax, I think, is maybe different from RLAX, or maybe it's the same. RLAX is like reinforcement learning, right? Or maybe Relax is about relaxation in some sense, like unrigidifying the model. Let's look at relax.python. Amber, relaxation. I don't want to Google that, but I guess I will. The Amber relaxer. Machine learning, I'll add. So this looks reinforcement learning-ish. So we have a controller, which is a recurrent neural network. I don't think this is a box. I think this is just saying that it trains a child network with architecture A to get accuracy R. So there's some controller in a child network, I think is what it's trying to say. And we're going to sample architecture A with probability P. And so we're sampling some architecture. I don't know how the architecture is represented. Maybe the architecture is some kind of graph or something along those lines, something you can sample. And then you're going to train a child network with that architecture and get some accuracy. And you're going to compute the gradient corresponding, the gradient of P and scale it by R to update the controller. The gradient of P. But P is the probability. What's the gradient of like half? I'm not sure. Why is it not the gradient of A? That I don't know. This could just be a crazy description. But it's something about CNNs. All right, I'll read that later. It's used for biology stuff. Okay, so there's an Amber relaxation thing. But I want to get to the model. Okay, and then we have a bunch of things in the model directory, including folding.py, features.py, data, modules, the PRNG. Modules might be important. I think people like to use the word modules in machine learning for the like little Lego bricks, the machine learning Lego bricks. Quat affine, maybe quaternion affine. R3 with a lowercase r might be the three-dimensional real space, although that would be sacrilegious to use a lowercase r. Okay, so here's model.py. It looks like we mainly have at the top helper functions, although we have a class that's called a run model, which is a container for Ajax model. There's some mode stuff like multimer. If we are in multimer mode, then we're going to define this forward function of batch. And we'll look up modules multimer.alphaFold, passing in some config model. And then return the model of batch, setting is training to false. So I think conventionally in Jax, model is the function that's returned by the model. It's like a callable function that runs the model. So I don't know if that's what this is. And it seems like maybe we have just some config that describes the model, and we are whatever multimer is doing is like inflating it or something. Otherwise, the forward function is we're just going to do the same thing, except we're getting we're calling it AlphaFold with the model without the multimer. And then we're going to return model of batch, setting is training to false, saying not to compute the loss, maybe because we're not training, and setting ensemble representations to true. So okay. So is the only difference here, so maybe we'll look at the implementations. One of the differences here seems to be the ensemble representations. I don't know if we don't use ensembles in whatever multimer is. And then we have this self.apply is we're going to call jax.jit on using the transform method from Haiku on the forward function, and then apply. Apply, I think, is NumPy thing. Is it just like apply a function? Apply along actions. Most efficient way to map a function over a NumPy array. So this person's just is looking at like doing a lambda. If the function you're trying to vectorize already is vectorized, then using that is much faster than anything else. Apply along axis. Maybe it's just like a vectorizing thing. Stop using pandas apply and start using NumPy's vectorize. Okay, well, I don't know what they are. I think that basically it's a way of applying a function along the vector. And that's what I will assume that this is, because I think Jax, by and large, is kind of like a fast implementation of the NumPy API. I don't know what Haiku transform is. I thought Haiku was dying. Is Haiku still alive? Okay, so new projects should adopt Flax instead of Haiku. Okay, so Haiku is like the precursor to Flax. So transform, passing in a function f and whatever this is, a list with an empty thing and apply RNG, transforms a function using Haiku modules into a pair of pure functions. All right, whatever that means. You get back some pair of pure functions. I don't know what the pair is doing, but it's, I guess somehow abstracting the Haiku modules. And there's this parameters function, init parameters, which is going to initialize the model parameters, presumably, since we're not training in general from some config, or not. So if we don't have self params, so I guess so you can pass them in, we're just going to generate them randomly. And we will create a mutable dictionary out of them. Passing in feet Where did feet come from? Okay, there it's passed into init params, and the feed is a dictionary of NumPy feature arrays as output by run model process features. Okay, so this is like purely random initialization. I was under the impression that initialization matters the way that you do it. I don't know if it doesn't matter that much or what. All right, and then process features. You're going to give it some raw features, which is I think this is just a union, not a union of lists, but it's a union, I guess, of train examples and feature dicts and a random seed. And it's going to return you a new feature dictionary. It processes the features to prepare for feeding them into the model. So raw features are the output of the data pipeline, either as a dict of NumPy arrays or as a tf.train.example, which I'm going to guess is just a container for like a batch of data. An example is a standard proto storing data for training and inference. Okay, so I guess this is the Google code base, and they store things in protos, and you read them off of disk somehow and run them and put them into this thing, and you pass it to your model. All right, and so what are we actually doing though? So this is just some checking whether, seems like what we ultimately call is example to features. If you pass in raw features in single chain mode. Otherwise, if it's not an instance of dict, if it's not a dict, then it's a train example, and we just call this function that's going to turn them into features. Otherwise, we're going to call example to features. Passing in the raw features, the config, and the seed. What have we changed here? Okay, we have NP example versus TF example. Okay, fine. And then eval shape is going to take some features, and it's going to return a Jax shape dtype struct, which I have no idea what that is, but presumably some way of wrapping up dtype information. A container for the shape, dtype, and other static attributes of an array. Okay, and so we're just going to, first of all, we're going to init the parameters when you pass in eval shape. And then we're going to call Jax eval shape with the features. So init parameters just did this thing where it stashed, I guess, a copy of the parameters and called some Haiku method. Okay, so we're going to call eval shape, passing in the self parameters, which are based on the features, and we computed in this method, and the features themselves, and that gives you some shape. Then you're going to log some stuff, and then we'll just return the shape. So really, this is just wrapping a call to eval shape. And then predict. It's going to take the features and a random seed, and it's going to return a mapping from string to anything. Makes a prediction by inferencing the model on the provided features. So we have this, now feat is required to be a dictionary of NumPy feature arrays. And the random seed is just a random seed. And you're going to get a dictionary of model outputs. I don't know why that can't be given a proper type, but that's how it is. I guess it's the model outputs that are any. So we're going to call init parameters in case that hasn't been done. And then we're going to call self apply, passing the self parameters and the random key and a feature. And that gives us a result. And then we have some block to ensure that benchmark timings are accurate. Some blocking is already happening when computing the get inference metric. Okay, so we have this JAX tree map, which I think we decided the other day is just going to iterate over. It's going to traverse some tree-like data structure and apply a function everywhere. And possibly gather the results, I'm not sure. And we've got this block until ready. So I guess it's just setting block until ready for everything in the result. And then we're going to call result update, get confidence metrics, and return the result. So it looks like, I don't know what apply is doing here. It's the thing that we got from Haiku. Where did Haiku go? So apply is we've JAX jitted, but that's a detail. We're transforming the forward pass. So this is some version of the forward function. And we're going to apply it, I guess, over all of the examples or whatever the unit of training data, not training, but inferencing data is. And the forward function is ultimately just calling model. So this apply is really implicitly a call to the model function. And let me take another look at the init params function. Init params. So init params is trying to be idempotent. So if we don't have, it only runs if we don't have params already. So you can't, like, I guess, re-init params. And this thing. Structures to mutable dict. Self init RNG features. Where's init with no? Oh, okay, here's init. So self.init is we've got this forward function, which is some Haiku thing. Basically, this is like initializing a neural network thing, some construction using neural networks, and then calling this its initialize function. I think. So whatever is returned by JAX so Haiku transform. So let's look at Haiku transform again. So for a function out equals f of star a star k. So star k is like passing in keyword dictionaries, I think, as a keyword dictionary. I forget what star a is. That might be like unfolding a tuple. This function returns a pair of two pure functions that call f star a star k explicitly, collecting and injecting parameter values. So params is given by init of RNG star a star k, and out is given by apply params RNG star a star k. So it's somehow like refactoring your function calls to make them easier to compose, I think is in principle what's going on. So that's that. Except we haven't learned anything at all about the model. And so where do we learn that? We must learn that in here, modules AlphaFold, I think, with this config thing. So AlphaFold.model modules, which is here. And we're seeing some machine learning stuff like softmax cross entropy, computes softmax cross entropy, given logits, and one-hot class labels. So one-hot class labels are, I think, just basically indicator functions. And softmax, I forget exactly what the function is. You basically exponentiate and divide. No? Am I thinking of the wrong thing? Yeah. No, I was thinking of the right thing. You exponentiate and then divide by the essentially all, the sum over the whole vector. And then I think they use logits to mean like the pre-softmax output. In statistics, logit is a function. The logit function is the quantile function associated with the standard logistic distribution. It has many uses in data analysis. So this is what I'm familiar with as logit. It's the log of the ratio of p over 1 minus p for some probability. For other types of logit, see discrete choice. For standard magnitudes combined by multiplication, see logit. So discrete choice, this is some economics thing. I don't think that they mean I don't think they necessarily mean this, do they? Also, what is the etymology of logit? It must be just logos, right? Logistic unit, by analogy with probit, coined by Joseph Berkson in 1944. I use this term logit for a log of p over q, q being the, I guess, the failure rate, following Bliss, who called the analogous function, which is linear on x, for the normal curve, probit. Okay, so it's a logistic unit in TensorFlow. We must feed the activation of artificial neurons in the layer. That I understand, but I don't understand why this is called logit. Isn't that a mathematical function? Logit is an overloaded term which can mean many different things. In ML, it can be the vector of raw non-normalized predictions. So non-normalized. So basically the output before normalization, and I guess before something like softmax or whatever the nonlinear activation function is, that a classification model generates. It's also sometimes used to refer to the element-wise inverse of the sigmoid function. Yeah, I don't know why these machine learning people, I feel like they're just trying to use the math terms, but they don't actually know it. Like there's a history of like people using terms that they don't really know what they mean, and so they've acquired like a second meaning. Kind of like if the grown-ups all started trying to use like kid slang, but only amongst each other, and so like all the slang comes out wrong and has different meanings because it's kind of like percolated. All right, so the softmax cross entropy, and we're computing softmax on the logits. The logits is just what's passed in here. We're going to sum, multiplying the labels by the logits. I don't know what type of thing labels are. I'm guessing labels must also be numbers. These seem like they must be vectors. I don't know what it means to star vectors. Maybe this is the element-wise multiplication, and then we'll take their sum. That's the where the negative of the sum is the loss, and then we're going to cast it as an array. I also don't know why that's cross entropy. So for discrete probability distributions with P and Q with the same support, this means that the HPQ, I think, should be the cross entropy function. We're just going to sum, well, we're going to have the negative out front. We're going to sum over all of the points in X, taking the probability of X and the log of Q of X, which I think should be 1 minus P. It's not clear to me that what they are computing is the cross entropy. Do I have ChatGPT open? No. Am I logged in? Or to Gemini? Yeah, so let's not call this cross entropy, but let's just copy the function and say, what does this do? And I'll add lots of exclamation marks. It computes the loss for a classification task, likely using cross entropy loss with softmax applied to the logits. This is the raw. Okay, so logits are the raw unnormalized output. We know that. Labels, this is expected to be a one-hot encoded vector. I think it is. I think that's what the code comment said. Or a probability distribution representing the true class labels. In a one-hot vector, the correct class has a value of 1. So it's just some indicator function. And then, we do have a log from the softmax. I guess I had forgotten about the log or didn't see it or something. This applies the log of the softmax function to the logits. The softmax function converts raw logits into a probability distribution over the classes. Taking the log of the softmax is typically done in classification tasks when computing cross entropy loss, which works with log probabilities to avoid numerical instability. Okay. And then we're going to multiply the true class labels, one-hot encoded, with the log probabilities. Since the labels are one-hot encoded, this operation effectively selects the log probability corresponding to the true class, and then we're going to sum them. So it's possible that since we're dealing with indicator functions and we're using the log here, that might be the same as cross entropy. I don't know where the 1 minus the probability term is. I'll say, what's the formula for cross entropy? Oh, so this is saying that yi is the true label, and p is the predicted probability for the class. So I guess that they're saying that Q is the, you know what, I was thinking of Q is a separate distribution, right? Two distributions of the same underlying sets. So I guess they're saying that Q is the distribution you are estimating, and P is the distribution that they're thinking of as truth. Okay, I'll buy that. All right, then we have sigmoid cross entropy, where we have now the log of the sigmoid function. Again, these are logits and not, I was going to say probits, but probits is not the sigmoid thing. Okay, whatever. All right, so we're just calling log sigmoid of the logits to get log p. And then here we do compute log not p, but we compute it as the log sigmoid of the negative logits. Log of 1 minus sigmoid x equals log of sigmoid of minus x. The latter is more numerically stable. All right, cool. And then the loss is we're just going to multiply negative the labels times the log p minus 1 minus the labels times log not p, and cast it as an array. Shouldn't we do some summation? I'm not sure. Okay, and then we have this dropout thing. We apply dropout to a tensor. Whatever star is, I'm not sure what that means in Python, I guess. So we give it the tensor a safe key, a rate, whether it's training in the broadcast dimension. And if we are training and rate in the, I guess the learning rate is non-zero, then we're going to take the tensor shape, make it a list, and call that shape. And if broadcast dimension is not none, then the shape at the broadcast dimension will be 1, which is maybe not broadcasting anymore. And the keep rate will be 1 minus the rate. So you pass in, I guess, the rate at which you're going to like destroy nodes of the network or whatever. And then we'll do some Bernoulli distribution, passing the safe key, which I think is maybe an RNG key. I'm not sure. The keep rate and the shape. And then we're going to return keep.tensor divided by keep rate, which I think is similar to what we saw the other day in probably was Flax. Otherwise, if isTraining is false, for example, then we just return the tensor itself. So I think the idea is that keep is a like matrix or a vector or whatever of ones and zeros. So this is going to zero out the some of the values of the tensor, and then we're going to divide by keep rate as a scaling thingamajiggy. And here's some dropout wrapper function. Create MSA feature. We'll expand the extra MSA into one hot and concat with other extra MSA features. We do this as late as possible, as the one hot extra MSA can be very large. I'm not sure what MSA is. It might be something related to, yes, it is, in fact. MSA protein folding. Multiple sequence alignment. Multiple sequence alignment is the process or the result of sequence alignment of 3 or more biological sequences, generally protein, DNA, and RNA. These alignments are used to infer evolutionary relationships via phylogenetic analysis and can highlight homologous features between sequences. Okay, so we are looking for some homologs. Are these all in the same alphabet? I don't know what I'm supposed to be looking at. What? So this Metak, Solak, I think these were all kings of the ancient Sumerians. Halma and Perko, definitely. So I don't know. So these are Ks. So this must be the aligned things, right? So we've got some sequences and in some encoding. This is not Gattaca, so I don't think this is DNA necessarily. But somehow we have noticed that these things align. And I guess we like try to look for places where they align. Given sequences, blah, blah, blah. Okay, so we do have a caption. The first 90 positions of a protein multiple sequence alignment of instances of the acidic ribosomal protein P0 from several organisms. So I guess these are, this is the same protein, if I'm understanding correctly, from different organisms. This is a ruler at the bottom. See, that's how you know that they were Mesopotamian rulers. Okay, so I think this is the same protein. These are the different organisms, maybe. And this is showing like how they have aligned or differ, and somebody went through with their highlighter and color coded it. I think. Let's see if we can find other pictures of MSA arrays. What if we say multi-sequence array? They all pretty much look the same. This is, at least this is giving me some more information. This is telling me that the rows, at least in this example, and probably also the previous example, the rows down are organisms. Mice and humans are different. Humans and chimps are basically the same. Rats and cows are mostly different. And they have some, whatever this thing is, some protein perhaps, and we see how they're different. In this case, they all seem to be pretty identical. Although cow kind of goes crazy in the middle here. And zebrafish is doing all sorts of stuff. Okay, so that's the multi-sequence array. I'm guessing that that's basically a piece of text, and you can predict it or use natural language processing on it. So AlphaFold iteration is a single recycling iteration of AlphaFold architecture. And I want to see the architecture though itself, but I guess we'll get to it. If I understand correctly, the AlphaFold architecture has this like loop where it like loops around 4 times. Maybe I'll try AlphaFold 3. I don't know if what we're looking at is the most up-to-date version. I mean, it's the GitHub repo is the most up-to-date version. I don't know what, of course, I don't know like how it diverges from the internal version. What if I just try AlphaFold architecture? Here's AlphaFold 2. Yeah, any of these I think should be fine. Although, hey. Okay, so you have some input sequence. And I don't know whether this is 2, 3, or 1, but this will be a starting place. Some input sequence, we have a genetic database search. And then we get some MSAs. I'm guessing these are data from the database. In fact, it looks like they are. And it seems like the MSAs can also just be pure input. There's some pairing. I guess we may, this looks like we're trying to pair the MSAs together possibly. And we have a structure database search, which gives us some kind of templates. I don't know if that's supposed to look like X-ray crystallography. Seems like reminiscent of what an X-ray might look like. And then we take these inputs. I don't know what the plus sign is. I guess maybe we add them together or we somehow combine them into some sort of MSA representation and a pair representation. And that goes into an evo former, which I'm going to guess is a transformer. Maybe evo stands for evolution. And it's going to output some stuff. It's going to output a single representation, depending on RC. I don't know what S here. We've lost the S parameter. This is maybe like just dimension reduction. We have a multiple S things with RNC, and now we get a single thing that depends on RNC, but not S. And down below, it seems like we are still using a pair representation. We have the same number of parameters. And then we take the output of both of these, and we recycle 3 times, I guess, at this stage. This is some sort of cleaning up. I don't know how we... maybe we're just recycling the single representation. Maybe we batch it up with other representations here. I have no idea. And then these go into some structure module, which has 8 blocks. I don't know what a block is. And we get a 3D structure. And it looks like, actually, I was incorrect here. The 3D structure also goes back inside. User input, database search, prediction model, and relaxation and output. So there's some relaxation phase. And I don't know what any of that is, but that's at least a little bit of an intuition about what we're going to be looking at. The AlphaFold iteration computes ensembled, averaged, that is averaged representations from the provided features. So you give it a bunch of features, and it's going to give, make averaged representations of those. These representations are then passed to the various heads. Passed to the various heads that have been requested by the configuration file. Each head also returns a loss, which is combined as a weighted sum to produce the total loss. So we have multiple heads. The heads each produce a loss, and they're combined. How they combine, they're basically summed, but not just summed, they are summed with weights. So they basically take that vector and multiply it by another vector. I don't know where those weights come from. They might be estimated. They might depend on the batch or whatever. Who knows? Somebody knows, but not me. And then the way that we're going to compute the averaged representations is below. So we have this call function, which is what? We've got this JNP as array, ensembled batch, passing the sequence length, or rather getting the sequence length and looking at the shape of 0. That's the num, I guess, of the ensemble, how many we have. And if we don't have enabled representations enabled, I guess, if we don't have ensemble representations enabled, then we do something about the batch stuff, which I'm going to ignore. We have this slice batch thing, which I think is probably just related to batching. I'll just pretend we're batching a single thing. And then we call embeddings and evo former. Compute representations for each batch element and average. So for each element of the batch, I guess the batch is the thing that we are averaging over, if I'm understanding this correctly. So we're going to call this embeddings and evo former, passing in the config that I guess configs the embeddings and evo former, and also passing in the global config, and we get this evo former module. Then we call slice batch, which is up here. It creates this dictionary, basically getting the items, putting them in the right structure, and then calling update. I don't know what this update function is. On calling update for the non-ensembled batch. Not really sure, but down here is where we call evo former module on the batch 0, which we get by slicing the batch at 0. And we pass in is training and get some representations. So these are the representations for each batch element. I don't know if this is now averaged or if we average below. Now we have this thing that says MSA representations are not ensembled. So we don't pass tensor into the loop. So we look at the representations object at the thing under the heading MSA, that gives us MSA representations, and we delete representations MSA. Maybe to save memory or to speed up computations somehow. And now we actually do the averaging, average the representations except MSA over the batch dimension. So if we have, so I guess we only do it if we have ensemble representations set to true. And we define this body, add one element to the representations ensemble. And I, comma, current representations is set to X, the thing that we pass in the body. The features is we're going to slice the batch at I. And we're going to call evo former module on the features, passing in whether we're training or not to get a representations update. Set new representations to an empty dictionary. Then we'll iterate over the current representations, set new representations at K to the current representations at K plus the representations update. And we're going to return I plus 1, I guess, so that we can call this in a loop, and the new representations. Have we just added a column? This seems like kind of crazy. So new representations is a dictionary. And so probably current representations is because okay, yes. So we're going to recall this in a loop. So I is the current loop counter. Current representations is the thing from the representations as of the previous loop. It looks a lot like you would set up for a recursive call. But since we have a loop counter, I'm going to guess it's not recursive. Although it may be. I still don't really understand what slice batch is supposed to be doing. Maybe it's worth looking at. So this is a dictionary. The keys are the VI for K. What is V? Oh, for V. Oh, okay. So for KV and ensembled batch items. I don't think I wonder if this was added relatively recently in Python, or if I just never used this kind of like list comprehension for dictionaries. No. I guess I just never used it. Use a dict comprehension, Python 2.7 or later. Okay, this is not at all new. I just haven't used it. Okay, so this is just creating some dictionary. The values are we're just taking the items, making a dictionary out of them. I thought that there was like, I thought you could just do that with like a call to dict of ensemble batch items. I don't really know how that's different, and I'm not sure what update is doing here. I guess that's updates some keys, maybe based on another dictionary, but I don't know where non-ensembled batch came from. It came from here. Let's verify what this Python dict update function is doing. I try not to use these explainer sites because they are poorly organized and they try to make you scroll through everything. But it doesn't seem like the Python docs have. I think you just I think you just give it another dictionary and it updates it. So I'll just assume that's what's going on. So it's just building a dictionary. But what is what's actually slicing? Oh, because it depends on I. Is that the idea? Yeah, that's the thing I missed. So this dictionary is just getting, I see. So the ensembled batch items has a bunch of stuff. We're just getting the, creating a new dictionary where the values are now, I'll think of them as a scalar instead of a vector. Although this might have been a vector of vectors before, and you're getting some other vector of other dimension back. But basically, you're taking a thing that mapped into vectors and now mapping it into scalars for that by the ith position, or something along those lines. At any rate, this is the loop. We're getting the curve representations. We're getting the batch. We're calling the Evo former module on it. And then we're just setting the new representations at K to be the current representations at K plus the representations updated at K. And doing this in a loop. And if these were just flat lists, then I don't know why you wouldn't just vectorize and have this be a sum. So these may be these may contain something else that has a plus overridden on them. Or it may be that the cost of vectorization is just not big enough. That's just faster to just iterate over them. I'm not sure. At any rate, conceptually what they're doing is clear. They have they're adding the updated stuff to the current stuff and returning that. It's not clear to me yet that that's an average. We have to divide by something, but I think we're building up to the average. And if we're running, if HK running init, I don't know what that means. When initializing the Haiku module, run one iteration of the while loop to initialize the Haiku modules used in body. So we'll call body with 1, representations. I don't know if representations is empty at this point. No, we got representations by calling it on the batch. Are we in a larger loop here? On batch 0. So this is like the what's the word? The start of the loop, the 0 case. The base case is the word I was looking for. So now we've done 0. We're going to, I guess, call body with 1 because we've done 0. Now we're on iteration 1. We get new representations. We throw away the iteration. And I guess we use this to initialize. Otherwise, for K in representations, if K is not MSA, so K is, I guess, some key. It's not necessarily an integer. We're going to say representations at K, at whatever the key is. So representations, I think, is probably a dict. These might be dicts here. I'm not sure. And we're going to divide by the what? We're going to divide by the D type. We'll call num ensemble as type representations of K dot D type. What? This should be a type. I don't know what it means to divide by a type. And at any rate, representations at MSA is going to be the MSA representation, which I think it just really pulled out so that it wouldn't get molested by any of the other stuff. And we said batch to batch 0. We are not ensembled from here on. But didn't you already ensemble? Heads is 0, and we're going to iterate over the head name head config in sorted self-config head items. And if there's no weight, we're not going to instantiate 0 weight heads, so we don't do this. Otherwise, the head factory is we've got this masked MSA head, a distogram head, a structure module, a predicted LDTT, predicted aligned error, and experimental resolved head. These are different heads. And we will have this dictionary, and we're going to index into them the head name. That'll be the head factory. So I guess this is just a dictionary of factories or something. Then heads at head name is we're going to have a tuple where we pass the config, and we also call the factory function. We'll set the total loss to 0. Because remember, at the the thing that we're ultimately doing is doing one iteration of AlphaFold. Set the total loss to 0. Set the thing that we're going to return, seems to be some dictionary, and we're going to set it to an empty dictionary. We're going to set the representations there to representations. I don't know why you couldn't do this in the same line. And then we are going to define the loss function, which is going to depend on the module, the head config, the return value, which is mostly an empty dictionary, the name, the filter ret, and filter ret is set to true. And if we are filtering ret, then value will be ret of name. Otherwise, we're going to use the whole ret. Ret is the return block, the return dictionary. And the loss output will be, we'll call the module loss function, passing the value in the batch. And then we will call the update function for the return thingamajiggy, for example, representations, passing in the loss output. And we'll set loss to be the head config weight times the return weight loss. So this is some weight for the head. This is now, I guess we're going to do a weighted sum of the loss functions across the heads, and we're going to return the loss. Head config weight came from where? It came from the config. I don't know if it's a trained parameter or is it like a thing that you just choose based on how you're feeling that day. I'm guessing it's maybe some kind of hyperparameter. And then we are going to iterate for name, comma, head config module in heads.items. So we're just going to iterate over the heads. And we're going to skip predicted LDD T head and predicted aligned error head until structure module is executed. I don't know why, but that's a thing that we're going to do. Otherwise, we're going to call the module, which we got from the heads list. So this is the module for that head, passing the representations, the batch, whether we're training. That's going to give us our return value. And if representations is in ret name, extra representations from the head used by the structure module. So we have some structure module. I don't know where it is. And we're going to call it representations update. And if we're supposed to be computing the loss, the total loss, we will get by adding the loss basically of this head for this batch or whatever it is. And then we're going to look at whether the predicted LDDT weight is 0. And this is going to add this thing that we skipped after the structure module is executed. Okay. So most of that makes sense. To me, at least, the thing that really did not make sense was up here. And I thought I would move on and then come back to it to see if I was just missing something obvious. And I don't even really remember what it was. Yeah, it's dividing by this type thing. Oh, what? Did I forget to... Okay, let's try that again. What does this code do? Let's start a new chat. Where is it? Here? It modifies the value associated with k. It divides the value by num ensemble. Oh. Wait, what? Oh. Okay. that is totally clear. I was reading this num ensemble as type as like a library call, but this is really the number, and then we're casting it as a type. And so I thought this was like a library call, and I thought that this was looking at representations of k and getting its type. So that this is what this is really doing is we are dividing by the same number all the time, but we are doing maybe float division or integer division, depending on what is appropriate for that type of thing. Okay, so the thing that we just looked at was one iteration of AlphaFold, and now here's AlphaFold itself, the AlphaFold model with recycling. I'm going to gloss over this pretty quickly. The impl is an AlphaFold iteration. Whatever prev is, maybe previous. We have this do call function with prev. I'm going to guess previous, recycle index, compute loss is set to whether you want to compute loss or not. And we're going to get some config stuff. We've got this slice recycle index is presumably going to give you like a dictionary slice, a dynamic slice in dim. And we've got this non-ensembled batch, and we'll call impl, which is the single iteration. So we've got this do call is, I guess, maybe going to do one call because I don't think we're yet looping over. It's going to call one thing in the iteration. And then, wait, what? Is this, oh, okay. So I think that, it's hard to say, but I think that we are two over from underscore call, which means that this like do call function is defined, I think, inside of the, of overriding the call operator. So we said previous to the empty dictionary, we get this embeddings and evo former thing, something about running, and then you've got a while loop here, but I don't think that's the main while loop, but we're going to call do call, get a return thing. If we compute loss, we'll compute it as ret equals ret of 0, and then a list containing the single element ret of 1. And if not, return representations will delete some stuff, and we're going to return ret. So so where do we use recycle index? We have this slice recycle index. We get this ensembled batch thing here. I feel like there must be some looping here, and I probably just skipped over it. I don't think it's this while loop here, but maybe it is. What is this defining? Self-config num recycle. That's for, it looks like this is for initializing the Haiku module. The output of AlphaFold iteration is a nested dictionary containing predictions from the various heads. Yeah, I'm not entirely sure. So where do we get prev? So prev starts out as 0, or as nothing. Do call prev. Yeah, I guess maybe this is it. If we're running init, we do one thing. We call this body function with 0. Otherwise, prev will be this while loop, lambda, looking at whether x of 0 is less than the number of iterations, the body in 0 prev. Otherwise, we'll set num iteration to 0. And what is this function that we're defining? That's just, I guess, defining prev, right? And maybe up here in do call is where we consume prev. Maybe it's I don't know. The prev seems like it's being used to consume the batch, so I'm not entirely sure whether this is one call or the entire loop, but I don't know. I'll assume that somehow it's the whole thing, and I'm not looking at the code closely enough to know really. Here's the thing for template pair stack. So I think I want to go, except I want to look at the attention heads, or whatever the heads are. So attention here is multi-head attention. We've seen some attention stuff from some of the other repos, I think Flax or something like that. We have this call thing, builds attention module. So the arguments are the queues, the queries. No. So the queue data is a tensor of queries of some shape. It's got batch size, number of queries, and queue channels. M data is a tensor of memories from which the keys and values are projected. So we're going to, I guess, project from the memories to the keys and values, and then we have a mask for attention, I guess, for the decoder operation. So we get the various dimensions. The queue weights we get from Haiku get parameter. Passing the string query weight, we have some shape stuff with number of heads, key dimensions. I don't know what Glorot uniform is. And similarly for the key weights and the value weights. I also don't know really what get parameter is doing. We're passing the number of heads, the dimensions, the D type. I don't know where the actual data are. Here's some Einstein summation stuff that we're getting by calling einsum. And we have, and then that gives us the Q, K, and V things. I think these are all matrices. And we compute the logits with this. I guess this is like some sort of multiplication by Q and K, by the keys and queries. And if non-batched bias is not none, then the logits, we're going to add to them the whatever expand dimension is non-batched bias, axis 0. And then the logits is going to be where is going to be the place in the logits where the mask is soft mask maybe. And then the weights we're going to get by calling softmax on the logits. We're using stable softmax. I'm guessing we saw some stuff in like the sigmoid function about stability. I'm guessing this is maybe numerical stability. And then the weighted average we're going to get by doing this. This should be some form of matrix multiplication with the weights and the values. And then we may be gating. And I'm not sure if gating is a little bit like clamping, like a noise gate, a signal gate. But it's maybe doing some stuff. Okay, so that looks like standard attention. What is global attention? I don't know. So it looks like we're global attention is referring to this paper, which I think is either the AlphaFold paper or something similar because it's cited in another method. And we have MSA, a column global attention. So MSA is the multi-something array or assay or something. So I think this is biology specific. This builds a global attention module. We have a Q thing, a tensor of queries, an M thing, a tensor of memories that we're getting keys and values from, and a Q mask, a binary mask for Q data with zeros in the padded sequence. So this is looking more or less like standard attention. I don't know what makes it different. Maybe is the Q mask different? We have a mask versus a Q mask. So mask is a mask for the attention. And Q mask is what? A binary mask for Q data with zeros in the padded sequence elements and ones otherwise. So it's everything that's not padded maybe. Then we have MSA row attention with pair bias. MSA per row attention biased by the pair representation. So the per row attention, maybe each row gets its own attention, like chimpanzee has an attention and rat has an attention or something. And we have some bias, and it's biased by the pair representation. So we saw that there was some pair representation in the architecture diagram. And I'm guessing bias is the machine learning literature has been using bias to refer to the translational component of an affine map. So I'm guessing that they're using bias in that sense, although I'm not sure. Call is going to take the MSA representation, an MSA mask, a pair act, which is the pair representation. I don't know what ACT stands for, ACT, and whether it's training. And we see some stuff here like layer norms that we didn't see before. Some random normal stuff. And we don't see like queries or values. And I'm sure that this is explained in the paper, but we haven't looked at the paper. And then we have MSA column attention. I'm going to guess it's going to be similar to row attention. All right. So here we're finally seeing some of the stuff. I'll just scroll through quickly. We see this global attention. We see a layer norm. I want to just kind of see what modules there are. We have triangle attention. There's something about like the triangle inequality as a constraint in AlphaFold. I don't know entirely what's up with it, but maybe this is presumably some attention head or module or doodad that is keeping track of like how well you're doing the triangle inequality or something along those lines. And we've got layer norm, random normal, and an attention thingy, an attention module. We have masked MSA head. Okay, so all the modules are here, kind of all in one file, a bunch of linear layers, it looks like. Predicted alignment error head. So it looks like, at least in AlphaFold, it's like a bunch of different heads. You now have this quad affine thing. I don't know how you decide. I guess there. Let's see. Predicted alignment head. Head to predict the distance errors in the backbone alignment frames. I'm guessing that now, because we are for a lot of this, we're doing kind of like feature stuff in a high dimensional conceptual or latent space. And at some point we have to translate that into something that we can render in 3 dimensions. And I think that is maybe why we're starting to see quat, which I'm going to guess is quaternions. So let's look at quat affine, which is here, quaternion geometry modules. This introduces a representation of coordinate frames that is based around quat affine object. It describes an array of coordinated frames. It consists of vectors corresponding to the origin of the frames as well as orientations, which are stored in 2 ways, as unit quaternions as well as a rotation matrices. The rotation matrices are derived from the unit quaternions, and the 2 are kept in sync. Okay. So I'm not, I want to know what R3 is, and then that'll be that. Transformations for 3D coordinates. Okay, so this is for three-dimensional geometry. So somewhere along the lines, we get the predicted alignment arrowhead. So that's going to translate us into 3D geometry, and we're not going to really see much of that. So that's an initial look at AlphaFold. I don't know. So I learned a couple of things. One is compared to the kind of like demo projects, we have a lot of different kinds of heads, and I'm going to guess that these were like carefully thought through, but also like heavily experimented with, and they kind of like figured out by some amount of cleverness, but also trial and error, which kinds of heads are needed and really help, and so on and so forth. And the details for like what they ended up with should be in the paper. But there's like a lot of this like sigmoid linear stuff, and that's kind of like the black magic, I think, of what makes a really top of the line model versus the kind of mom and pop stuff. All right, so I'll stop there. Thanks for watching.